Hi, my name is Nina Milliken, and this is the first video in a series on nanoscale computation for the SEAS initiative here at NC State. First, what is nanoscale computation? Broadly speaking, computational science and engineering seeks to reproduce the behavior of a system by using a computer to simulate the outcomes of a mathematical model associated with the system. In the context of material science, computation can be used to study the properties of atoms and molecules and larger structures such as polymers, biomolecules, and nanoparticles. Why would we want to use nanoscale computation in conjunction with experiments? There are three obvious motivations: cost, in the form of time and money; safety, and perhaps most importantly, in the identification of information at experimentally unprobable scales. Let's consider the first motivation, cost. The time and money associated with materials discovery can be extremely high. As an example, in my work on directional solvent extraction, we are trying to identify an organic solvent that is capable of simultaneously absorbing water and rejecting salt ions. Such a solvent can be used in energy-efficient saltwater desalination. Unfortunately, many of these candidate solvents can cost thousands of dollars. So any information on solvent efficacy we can glean from computational experiments has enormous potential in terms of time and money saved. Let's consider safety. It isn't uncommon to do research on materials that are highly corrosive, toxic, or explosive. As a contrived example, consider the compound dimethylmercury. Dimethylmercury is a small organometallic compound infamous for its extreme lethality. Perhaps a biochemist is interested in the interaction between this compound and a biomolecule, such as a protein. Any information that can be determined using simulations can potentially reduce the number of necessary physical experiments and thus reduce exposure to this highly toxic chemical. Finally, let's consider the third motivation, observing the unobservable. Experimental resolution has been rapidly increasing for decades, but there are still phenomena that happen at length scales so small and time scales so short that they are still beyond the resolution of even the most advanced instruments. Simulations can be used to shed light on phenomena such as enzyme mechanism, solvation shell structures, and polymer conformational changes. In this module, we will consider three nanoscale computational techniques. In order of decreasing resolution, we will discuss density functional theory, all-atom molecular dynamics, and coarse-grained molecular dynamics. Density functional theory, or DFT, is a quantum mechanical method that can be used to study the electronic structure of atoms, molecules, and condensed phases. DFT is the highest resolution theory that we will be discussing. It can account for individual electrons in a material, and it considers both classical and quantum effects in its calculations. However, its application is limited to small systems of a few dozen to a few hundred atoms. All-atom molecular dynamics is a completely classical method that treats individual atoms as dimensionless point charges that interact with one another via electrostatic forces. This technique iteratively solves Newton's equations of motion to determine atom positions and velocities, and it can be used to investigate the movement of atoms in systems of millions of atoms. Coarse-grained molecular dynamics is another classical method similar to all-atom molecular dynamics. However, as the name would suggest, individual atoms are embedded into larger, coarse-grained beads. This coarse graining permits the exploration of larger systems for longer times at the expense of resolution. Unfortunately, coarse-grained potentials are typically highly specific and must often be tuned manually. In conclusion, we use nanoscale computation to investigate phenomena efficiently, safely, and at scales yet unprobable by experimental means. All simulations must make assumptions which will dictate the resolution of the system under scrutiny and the time and space scales investigable with a given method. In future videos, we will be discussing in greater detail two methods: density functional theory and molecular dynamics.